Okay, so in the prior couple of videos we have been working on the problem of a rolling cone, and the specific problem that we were trying to solve is if a regular cone is rolling on a horizontal surface, then find an expression with a given angular velocity, then find an expression for the velocity of an arbitrary point on the circumference of the cone's base circle. So the problem statement goes as follows. So to draw a sketch and explain it better, so let's say that this is a regular cone on a horizontal surface, and the angle of the cone is beta, and the vertex of the cone is at a point O, and let's say that this axis goes through the point O prime, and the cone is rolling without slipping on the horizontal surface. So cone rolling without slipping. The radius of the base circle is r, small r, and the rolling angular velocity is omega. At any arbitrary instant, the point of contact of the base circle with the ground is at C, and we have let's see. So this is the rolling cone, and if you take a view of this base circle from the using this projection AA prime, what you would see is essentially a circle. Okay, so this is view AA prime. Now this point on the circle is the center of the circle is O prime, and the point on the circle that is touching the ground is C, and if we draw a line through O prime and C, then it goes through the highest point on the circle, and with respect to this line we define the position of an arbitrary point on the circumference of this base circle, and the location is given by this angle phi. So you can imagine that this angle phi, or rather phi dot, represents the spinning of the cone about its axis of symmetry. The axis of symmetry, by the way, in this view goes through the point O prime and is perpendicular to the circle, perpendicular to the surface of this page in this view. Now if you take a top view of this cone, let's call that view B prime, what you would see is the following. You would see the cone would look like this. Okay, and this is the point O prime. Sorry, this is the point O, not O prime. O prime is over here, and that's the axis of the cone, and so this is the view B prime, right? So you would see that this point O prime is tracing out a circular path. So O prime will trace out a circular path. Let me just take this one out so that this is the letter O and this point is the letter O prime. And the point P would be somewhere here on the circumference. And so this point O prime would be tracing a circle, and its velocity would be tangential to the circle. So that arrow that I have drawn is the velocity of the point O prime. Okay, and since you are viewing this from the top, you would see the axis of symmetry O prime turning with an angular velocity of omega. And as that happens, as it turns, the cone is also going to spin about its axis of symmetry, and that spin is given by phi dot. And if you go over our previous videos, you will find that we have derived an expression for phi dot as a function of omega, because indeed it is a function of omega, since it is rolling without slipping, and rolling without slipping at a certain speed automatically causes a spin about its axis. So we have determined that this phi dot, that is the spinning speed, is equal to let me see, it's omega divided by sine beta, where beta, as I have shown over here, is the angle of the cone. Now our goal is to find the velocity of the point P, and in this particular video we will again consider a rotating reference frame. So rotating reference frame will be used. The specific rotating frame that we are going to use in this video is a rotating frame which has the following orientation. It has an x-axis, or you can say a unit vector I, small I, along the axis of symmetry. Okay, it has a unit vector small j which is into the surface of this page in this side view, and it has a unit vector k which is pointing like this. So this ijk is the rotating frame that we are going to use. Now if we take this ijk and view it along the AA prime view, what we would see is j is like that, k is like this, and I pointing outwards is like shown. So I is along the axis of symmetry, I cross j gives k, so that's the right-handed coordinate system. Here j is into the surface of the page, I cross j gives k. And if you now project those same unit vectors over here on the view B prime, the I unit vector would be in this direction, j would be along the velocity of OO prime, so that's going to be j, and k is going to be directed, it's also going to be on the surface of this circle, but it's going to look like it's along the axis of symmetry, but it is actually perpendicular to the axis of symmetry, right? So this is going to be k. K is actually not along the axis of symmetry, it is perpendicular to the axis of symmetry, as you can see here, right? So k is perpendicular to the axis of symmetry. That is obvious over here as well. This is just that because of this view, it seems like k is along the axis of symmetry. The unit vector that is actually along the axis of symmetry is I. Okay. So you can see here what we are doing is we are taking a different rotating coordinate frame to solve that same problem that we have solved in the prior couple of videos. So the reason we are doing this is because, as we have mentioned at the very outset, that the goal of these videos is to provide you with various different techniques of dynamics, certain approaches that help us understand dynamics better, especially when it comes to rigid body dynamics. And one of the things, and one of the approaches rather, that helps us understand rigid body dynamics better is to take these problems and solve them using various approaches. Okay, and one of the ways to try different approaches is to consider different rotating reference frames if you can, and that is the goal. That is the reason why I have chosen a different rotating reference frame. Our previous rotating reference frame was like this. It was such that our unit vector I was directed along the line of contact of the cone with the ground. J was directed into the surface of the page in this view, in this side view, and K was always directed upwards along the vertical. Now it's a bit more complicated to show this I, J and K on this projection, but you can show the I, J and K on this projection quite easily. That is the capital I, J and K, which is our previous rotating reference frame. So our previous rotating reference frame had I like this. See, along the line of contact of the cone with the ground, J was perpendicular to that, and K was this is a little bit busy here, but K was perpendicular to the surface of the page when you took a diagram, when you took the top view, that is the view PB prime. So both were rotating reference frames. So previously we used capital I, J, K. We have used this triad. Now we use I, J, K. This triad or this triad that we have shown here. Okay, so goal is to find VP, and we know that if I can express the velocity of a point on a rigid body with respect to the velocity of another point on a rigid body, then we have some very specific results there. So VP is equal to VO prime plus VP with respect to O prime. That is the general result, and this just comes from the principles of relative velocities. In this case we have VO prime, and then P with respect to O prime gets split into two parts. One part of the relative velocity comes from the fact that a relative velocity is contributed by a rotating frame. So if you're viewing a motion in a rotating frame, then you have a relative velocity that comes from just the motion of the rotating frame itself. So omega cross rho p with respect to O prime. So that's that. And then if there is a motion of the point of interest within that rotating frame, then that is included, that is added. So this is the relative velocity owing to the fact that the frame is rotating, and this is the relative velocity owing to the fact that within the rotating frame the point P has a velocity with respect to O prime. So this is again P with respect to O prime, but this is a velocity within the rotating frame. So just to clarify, what I have written here is rho dot P with respect to O prime, okay, in the rotating frame. So that is what I have written here. It's a little bit busy here. Now VO prime, let's take these vectors one by one. VO prime is the velocity of O prime, and deliberately we chose the point O prime as our reference point with respect to which we are going to express the velocity of P. We deliberately chose O prime because the velocity of O prime is rather easy to express even in this ijk, small ijk coordinate frame, the coordinate frame that we are using now. And so that velocity is h cosine beta times omega, and it's in the direction j. So it's in the direction j, this red vector. The magnitude of this vector is nothing but the angular velocity times this distance. Now this distance, if I denote the height of the cone by h, then this distance is h cosine beta, because it's the projection of this height on this horizontal on a horizontal surface. So h cosine beta omega j is the velocity of VO prime. Okay, and by the way, we can always express h as r divided by h is equal to tan beta. So this relates r and h. So if you are given r and beta, you can find h. If you are given h and beta, you can find r, and so on. So that's VO prime. Now the angular velocity, keep in mind that when you are using this equation to express the velocity of a point with respect to another point, and you are using a rotating frame, the angular velocity omega refers to the net angular velocity, the total angular velocity of the rotating frame. So let us consider what is the angular velocity of the rotating frame. Note that this rotating frame I, j and k, shown over here as well, I, j and k. So this rotating frame, what it does is so let's see, this is I, j and k. It turns with the point O prime. So as O prime turns, I, j and k turns. So I, j and k basically has the angular velocity of O prime, which is omega. Now the angular velocity of O prime, however, is in the vertical direction, right? So if you consider the angular velocity vector, so here is my I, let's say this is j and this is k, okay, and this is the axis of symmetry. Now the angular velocity of the cone due to its rolling is in this direction, the vertical direction, and it is by an angular velocity omega. So the vector of the angular velocity is this way in the vertical direction, and if this angle is beta, which is the angle of the cone, then this angle is also beta, right? So if this angle is beta, then you can say that in terms of, if now I'm trying to solve this with solve this problem with small ijk as my unit vectors. So I want to express all the vectors in terms of small ij and k. So then my omega, I cannot write it as omega k anymore, because that k is the vertical direction k, which used to be my previous ij and k unit vectors. My current ij and k unit vectors are tilted from there. It is still rotating with the angular velocity omega, but it is tilted. Okay, so then I have omega to be equal to the angular velocity omega cosine beta k plus the angular velocity omega sine beta I. Right, so this is my angular velocity vector now. So you see there has been a subtle change because of considering a different rotating frame. Now let's then figure out rho p with respect to O prime. So this vector is understood if you now go to this view, and so p with respect to O prime is a vector going from O prime to p, and here are our I, j and k coordinate frame, and of course the distance of p from O prime is r because of the radius. So then you can say that rho p with respect to O prime is r sine phi j plus r cosine phi k. So r sine phi j plus r cosine phi k, that's the vector p with respect to O prime. Okay, so we have figured this vector, we have figured out this vector, this one. Now all we are left with is this vector. Now to find this vector, we first get an understanding of what this vector means. This is the velocity of the point P within this rotating frame. So imagine that you are in this rotating frame. What velocity would you perceive the point P to have? So imagine this I, j and k that is on the face of this base circle, and they are maintaining this their direction, that they are of course rotating with the rolling cone. But with respect to this I, j and k, the movement of the point P is going to be just the spinning motion. So if you were I, j and k, and if you had sensors along I, j and k, okay, and you were viewing the point P, then all you would perceive is the circular motion of this P due to the spinning of the cone about its axis of symmetry. So in order to find that out, what we do is we differentiate this position, but when we differentiate this position, we don't differentiate j and k. If we differentiated j and k, then that would be the net velocity of the point P. Okay, rather here our goal in this vector is to find the velocity of P with respect to O prime in the rotating frame. So we are within the rotating frame. Because we want to find what is the velocity perceived within the rotating frame, we are not going to consider the motion of the rotating frame itself. So rho P with respect to O prime dot in the rotating frame, which is this last vector, is going to then be r phi dot cosine phi j minus r phi dot sine phi k. And the important thing is that in this particular velocity calculation, I did not differentiate j, I did not differentiate k, although I have considered I, j and k as a rotating frame. I did not do that because by not taking the derivative of the unit vectors, I am isolating the velocity of p with respect to O prime within the rotating frame as perceived from inside the rotating frame. So we have this expression. So we have all the three vectors, or rather all the four vectors, 1, 2, 3 and 4 vectors determined. And so we can now come up with the overall expression. We need to do some geometry to find the expressions. So we will find the expressions next. So then velocity of p is equal to, let's first write the three vectors. Velocity of O prime plus omega cross rho p with respect to O prime plus rho dot p with respect to O prime in the rotating frame. Okay, so V O prime is h cosine beta times omega j plus omega is omega cosine beta k plus omega sine beta I. So I'm sorry, I'm just referring to both this vector as well as this symbol by omega, but really they are that. This omega represents the angular velocity of the rotating frame, and this is also omega. I mean, this is another Greek letter. You could say that this is capital omega. Here we are using this omega to represent the angular velocity of the rolling of the cone. So a slight misuse of terms, but I hope you'll be able to follow. Now this rho p with respect to O prime is r sine phi j plus r cosine phi k and then we have the velocity within the rotating frame, and that is plus r phi dot cosine phi j minus r phi dot sine phi k. Alright, so let us carry out the cross products and do the addition. So I'm going to just cluster all the terms that have j in them together first. So h cosine beta omega, that's a j term. K cross k is going to be 0, k cross j is going to give me I cross j is going to give me k, and I cross k is going to give me a j. So I will have a negative r capital omega sine beta cosine phi j, and this negative is because I'm going to do I cross k, and our convention is that we have a right-handed coordinate system where I cross j gives k, j cross k gives I, k cross I gives j. Here we are going in the reverse direction, and hence the negative sign. And then we have plus r phi dot cosine phi j. I should remove this j from here. Okay, Then let us put together the terms that have k in them. So we have this term that has k in it, so negative r phi dot sine phi, that has a k. This I cross j is going to give me a k, so I have plus small r omega sine beta sine phi, and that's the k terms, the terms in the direction k. And then let us see which terms have I in them. So k cross j is going to have a I in it. K cross j gives negative I, so we will have negative omega r cosine beta sine phi I. Okay, so that's the velocity Vp. Now what we'll do is to verify that indeed this method is correct and it has given the correct results. We will try to reconcile this solution with the solution that we had in our previous video. Remember that in our previous video our I, j and k looked like this. So this was our capital I in the horizontal direction, this was capital K, and capital J was directed into the surface. Now we have a subtle difference. We now have I like this, making an angle beta. We have K like this, making that same angle beta. And we have J in the same direction as capital J. So this is the only difference. Basically our new rotating frame is similar to the previous rotating frame. It's only that this rotating frame has been turned by an angle beta. And so there is a mapping between this small ij and k and capital Ij and k. One thing that you can see is that small j is equal to capital J. So the j component, you can just directly say that this is the component in the capital J direction. What we are going to do is express this vector in the capital Ij and k using the capital Ij and k unit vectors. Small I can be found out quite easily if you take this capital I and project it, and if you take this capital K and project it on the I direction, then small I is capital I cosine beta plus capital K sine beta, and then small k is found by similarly projecting the capital K onto small k and then capital I onto small k. So it's going to be capital K cosine beta minus capital I sine beta. So this is essentially our mapping, and you can consider this to be nothing but the transformation from one set of coordinates small ijk to another set of coordinates capital Ijk, and you can consider this transformation as derived like this using just the vector projections, or you could also use a rotation matrix. Rotation matrices are quite frequently used. This is simple enough that we could just derive it. So with this then, let us determine all the vectors in all these different directions. So we have so then Vp is equal to, so I'm going to express everything using R and beta and this capital omega. I'm not going to use H, and we have the mapping between R and H. R is H tan beta, or rather H is R divided by tan beta. So substituting that here, R divided by tan beta times cosine beta omega minus r omega sine beta cosine phi plus phi dot is omega divided by sine beta, so r omega divided by sine beta cosine phi. And since we are expressing everything using the capital IJK directions and small j is equal to the capital J direction, so hence we have this expression. This expression comes directly from this j component, and I have just replaced the small j with capital J. Now the next one is k, and that k, if you now apply this transformation, you notice that k has got components in the capital K direction as well as components in the capital I direction. So let us take the component of this in the capital K direction first. So we will have let me just simplify this. So you will have plus minus r omega over sine beta sine phi plus r omega sine beta sine phi, and let's substitute for k. We will have capital K cosine beta minus capital I sine beta, right? And then we have minus omega r cosine beta sine phi, and we can replace this I by this expression. So capital I cosine beta plus capital K sine beta. Okay, so let us continue with this simplification on the following page. So we have then Vp to be equal to you have in J, you have R omega as a common term. So let me just do, and this is sine beta divided by cosine beta. So this is going to become r omega sine beta, r omega divided by sine beta times cosine squared beta. So you would have the following. You would have r omega times cosine squared beta over sine beta minus sine beta cosine phi plus cosine phi divided by sine beta, and this would multiply with j hat. Now if I take all the k components, I would have there is a sine phi that I can see is going to be a common term, so minus 1 over sine beta plus sine beta cosine beta minus sine beta cosine beta. Yep, and oh sorry, there is another term here, I forgot to add that. So r omega sine phi, so that's a common term. And so indeed, if you take all these k terms, you will see that there is a common factor of r omega sine phi. So that's why I took this r omega sine phi as a common factor, and then these two cancel. Okay, so we are left with a rather simple term. And this actually should be cosine beta, because indeed cosine beta multiplies here. And then if you take the I terms, you would have, let's see if there is any other. Okay, so if you take the I terms, what you would get would be the following. You would have sine phi, sine beta would cancel with this guy with a negative sign. Minus sine squared beta sine phi. This would become a positive because you have a negative here, another negative here. And then you would have minus cosine squared beta sine phi. And the common factor out would be omega r, and the unit vector is capital I. So one thing that you would see over here is that sine squared beta sine phi and cosine squared beta sine phi, they both have negative signs, so they will add up to give you minus sine phi. And when you add with this plus sine phi, then this whole term cancels out. Okay, so then proceeding forward in the last step, we will have and I'm going to take cosine squared beta and sine beta as common factors. This is going back to the first term, which represents the component of the velocity in the j direction. So it's going to be 1 minus sine squared beta over cosine squared beta cosine phi plus cosine phi divided by cosine squared beta. And that's in the j direction. The I component has completely cancelled, and so what we have is one component, the one other component, there's a component in the k direction, and that is minus r omega sine phi cosine beta over sine beta k. Okay, and now in the last step we do a slight trigonometric simplification, because one thing that you would see is that if I took cosine phi divided by cosine squared beta as a common factor, then I would get basically 1 minus 1 minus sine squared beta divided by cosine squared beta, which is going to become 1, and so this will reduce to 1 plus cosine phi, yes, 1 plus cosine phi j minus r omega sine phi cosine beta over sine beta. And that's the expression for Vp. And if you double check with the velocity expressions that we have calculated in the first method, where we took capital Ijk directly as our rotating frame, we got the same result. So this confirms that the velocity that we have found out with this method is indeed the correct velocity, because once we did the coordinate transformation and represented the velocity in the capital Ij and K, we did get the same answer as before. So that concludes this video, and we will proceed to other problems in the next video onwards. Thank you.